All right, welcome. So we've put in all this work training our AI model, right? We've fed it data, we've taught it to see patterns, but now we hit the most important question. Did it actually learn anything? How do we even know if our model is an A-plus student or if it's totally flunking out? Let's dive in and figure out how we grade our AI. Really, you can think of it just like a final exam for a student. After all that training, which is basically the AI going to class and doing its homework, we have to give it a test. A test with questions it has never, ever seen before. Our job is to set up that test, and then, of course, to grade its answers to see how well it really knows its stuff. Okay, so before we can even hand out the test, we need to get the exam room ready. And in the world of code, this means we've got to set up our environment and our data in a very specific way. This is all to make sure we're giving it a fair and, most importantly, an accurate evaluation. This is our four-step prep work, our checklist. First, we load up our data. We're using the classic iris flower data set here. Now, this next step is absolutely crucial. We split that data. One part is for training the model. Think of it like a practice test. And we keep the other part, the test set, completely hidden from the model. After the training's done, we use that unseen test data to make predictions. You see, that separation is the real key to a fair grade. And now, for the moment of truth. The very first and probably most common way we grade our AI is by looking at its final score. We call this accuracy. It's like that big, bold percentage you see at the top of a graded test. So what is accuracy really? Well, it's super simple. It's just the percentage of times the model got the answer right. If it made, say, 100 predictions and got 90 of them correct, boom, its accuracy is 90%. It's a really straightforward, easy-to-understand number that gives us a quick snapshot of how well our model did. And check this out, in the code, calculating this grade is ridiculously easy. We use a popular library called scikit-learn, and it's literally just a single function, accuracy score. We just hand it the real answers, that's our y-test, and our model's predictions, and it does all the grading for us. So cool. So what score did our model get on the iris dataset? A perfect 100%. Wow. Every single flower in that hidden test set was identified correctly. I mean, that's a fantastic result. But while that sounds amazing, we've got to ask ourselves, does this one number, this 100%, really tell us everything? I mean, what if some mistakes are way, way more costly than others? A perfect score is obviously great, but in the real world, models are going to make errors. And when they do, we need to understand exactly what kind of errors they're making. And that brings us to our next tool, the confusion matrix. Okay, so if accuracy is the final grade on the report card, the confusion matrix is like going through the test paper question by question to see exactly what the student got wrong and maybe even why. It helps us find the patterns in the mistakes. To put it simply, the confusion matrix is just a table that gives us a much more detailed breakdown. It doesn't just tell us that the model was wrong, it tells us how it was wrong. It literally shows us where the AI got, well, confused. And this right here illustrates perfectly why that detail is so critical. Just imagine a model that's designed to detect cancer. A false positive, where it says you're sick but you're actually healthy, that's a huge inconvenience, right? But a false negative, where it says you're healthy but you are in fact sick, well, that could be a fatal error. Accuracy just lumps these two very different mistakes together. A confusion matrix splits them wide apart so we can see them clearly. And just like with accuracy, the code for this is incredibly simple. It's another one-line function, confusion matrix, and it takes the exact same things, the truth and the model's predictions. That's it. And this is what our model spits out. This table is the confusion matrix. Notice how all the numbers, the 19, the 13, and the other 13, are all lined up perfectly on that diagonal from top left to bottom right. And all those zeros everywhere else, yeah, they're telling us something really, really important. So let's actually break down how to read this thing and really understand why this deeper level of grading is absolutely critical if you want to build AI systems that, actually work reliably in the real world. The easiest way to read this is to get the layout down. The rows, they represent the actual honest-to-goodness truth. The columns show what our AI predicted. So that diagonal line running through the middle, that's the good zone. That's where the prediction perfectly matches the truth. Any number that falls off that diagonal is in the error zone. Now, because our model got that perfect score, all of our predictions land squarely on that diagonal.
If, for example, the model had mistaken one versicolor flower for Virginica, we'd see a little 1 pop up in one of those off-diagonal boxes. It would instantly tell us the exact nature of that mistake.
This quote just nails it, doesn't it? Accuracy gives you the big picture, that one final score. The confusion matrix gives you the diagnostic details. It shows you exactly where your model is strong and, more importantly, where it's struggling. You really need both to get the full story. So I'll just leave you with this final thought to chew on. When could a model with 95% accuracy actually be better than one with 99%? Well, the answer goes right back to our cancer detector example. It's not just about the final score. It's about the cost of the mistakes. And understanding that is exactly why we always need to look beyond a single number and grade our AI on the details that truly, truly matter.